Okay, we got final 2 bits for the scanner. Okay, 2 bits, and then we're going to finish that, and then we'll go on to the syntactic analysis for the parser, which will be more interesting to study for the next few weeks. But let's finish the scanner first of all, to make sure everybody's okay. What we have done so far, don't lose the big picture. You will see a similar flowchart in the beginning of the scanner lecture, but let me just review very quickly. Okay, basically, for you as a compiler writer, you have to specify regular expression. Okay, given certain language you would like to recognize, and then from the regular expression you can apply so-called the well, basically you can use epsilon transition, etc. Basically the last part that we talked about last Wednesday. From there you can go to epsilon NFA, and then from epsilon NFA you can turn that into NFA. Okay, of course this is called subset construction. Okay, and then oh, you know what? I think DFA. Thank you. So now today we want to go a little bit further about the picture. Okay, basically that's what we have done so far. Make sure you're comfortable with every step that's going to be covered in your quiz number 1 on Wednesday. Okay, I would say maybe you want to get comfortable with doing subset construction. Maybe, maybe not. We'll see. Okay, so today we're going to do 2 things. Okay, number 1, we're going to see the DFA that you actually got from this entire process is not going to be guaranteed to be minimum in its number of states. It's not guaranteed. So the idea would be the fewer states you have for DFA, the better, because the memory space might be sensitive to your particular application, right? So now we want to have a process to say we want to basically got the same DFA with an equivalent behavior, but somehow maybe with fewer states if possible. So it's going to be the minimize process that we're going to do. We're going to minimize the number of states in the DFA, whereas the resulting DFA will still be equivalent. That's number 1. Okay, we're going to do that first, and then finally we're going to see, just get some vague idea about once you get your DFA, how you can turn that into code. And this will be the final scanner that we're going to get. Okay, of course, for your projects later, you really don't have to come up with this code yourself. You don't have to. Any tool, like Antler, given expression like this, like a regular expression, they can automatically generate code for you to use, so you don't have to. But for completeness, you should really have some knowledge about how the code should look like to see what the critical features might be. We'll just go over that quickly. The textbook mentioned about 3 different interpretation strategies for turning your DFA into the code. I'll just talk about one of them. For the other 2, you can look at them for the breadth of your knowledge. Okay, that's going to be the hopefully the first half for today. And then we're going to draw the conclusion on the scanner and then move on to parser. After parser, we still have to do a little bit review before we can go on to some new stuff. But we'll do one thing at a time. Okay, that's kind of the roadmap. Any questions until now? Okay, good. Question. When you took your 2001, did you guys learn about how to minimize the number of states in DFA? Any one of you did? Oh, you guys did? Oh, I'm curious. You did? About minimizing the number of states in DFA. You don't remember. Anyway, I suspect usually this might be like an optional topic for instructor for 2001, but let's do it. Okay, I think it's kind of nice, kind of like a nice algorithm to think about. Okay, the motivation is very easy. So we talk about from regular expression to epsilon NFA, from epsilon NFA to DFA. But now the DFA we have from this process is not necessarily minimum in its number of states. So we want to really minimize. Okay, and the motivation is pretty straightforward. Basically, if the memory is sensitive, you better minimize your number of states, right? For example, maybe you want to store somehow your DFA implementation into some cache memory where the space is really limited. So the fewer the better. Okay. In some examples that we're going to see, you can actually shrink down the space, state space by half, which is pretty good. Okay. So I would say it's like a technique that's worth learning. Okay. The way I'm going to do it is I will just go over the algorithm like a pseudocode with you. Hopefully that's straightforward enough. It's basically adapted from your textbook, but I found it a little bit not so intuitive. I changed that a little bit, but I think the idea is still the same. Let's see how that goes. But if you study a textbook, you should cause no harm. Let me go over just line by line very quickly to get some idea, introduce some terminology. And then we'll go over 3 different examples, and they'll give you some exercises. Okay? I think that'll be a nice way to introduce you to this algorithm. It's not a very long algorithm, just a single page. Okay, think about the input and output. The input is simply just going to be a DFA. So now DFA may be simply the output from our entire process. Maybe its original source for the DFA is simply some regular expression. Or it could be just DFA that you were just given. Okay, either way. And for the DFA, you got the states, you got alphabets, you got transition, you got initial state, you got also accepting states, right? Very standard representation. And look at the output over here. The output is going to be n prime. It's most likely going, well, it can be simply just n, identical, which means there's no scope for minimizing the number of states. Maybe it's already minimum. That's one case. Case number 2, it could be n prime. Number 1, it should be minimum the size of Q, which means the number of states should be minimum. But the second part is extremely important because you cannot just try to minimize the number of states, but you just get something that's totally behaving differently, right? So it should be equivalent behavior as n. Okay? When we show you the algorithm, we just give you some intuition about why this will work, but we don't really try to prove it, right? It's kind of maybe tedious to prove. Also, the textbook doesn't really prove it. I think if you're curious about the proof, if you Google around this algorithm, you should be able to find the proof. Okay. Okay. Any question about input and output? Input is DFA, output just another DFA. They may or may not be the same. Okay. Let's see what we're going to do. Okay, I'll just go over line by line. First of all, don't worry if you cannot follow. Just get some basic sense. Because we're going to run this algorithm on different examples. Okay, first of all, we're going to get P and T. Basically, P is simply means a partition. Okay, so how does a partition look like? I'll give you a typical example, so it's easier for you to imagine. So now, think about, for example, if you have, for example, let's say, if the Q of your DFA is simply, just for example, let's say S0, S1, S2, S3, let's say you got 4 states over here. When I say a potential P, think about how you can partition the set of states over here. For example, I might say I want to partition this into a first set. I want to partition this into a second set. In which case, P would be something like this. Would just be a set of sets, S0, S1, and then S2, S3. Okay, you can think about this is a so-called partition, right? This is one partition, this is another one. Okay, another way to think of it, if you're doing software testing before, we talk about when you want to draw test cases for your system, you want to focus on equivalent classes. Okay, I'll just mention the word first. Equivalent classes. Equivalence class, which means eventually what we really want to do is to get to as few partitions as possible, such that all the states in this particular partition will be considered as the same. Okay, abstractly speaking. Okay, I'll just mention that and then try to come back to this point once we go over some example, right? These are the insights. You can think about each states in this set or equivalent class is considered as equivalence for their behavior. Okay, just talk about the shape of the partition. Okay, we're going to do this. A very possible partition would be, give you one extreme case. If this is our input, let's say if this is the Q, right? Input states. If eventually we find that this is the best partition you can get, for example, eventually if the algorithm tells you the best we can find out is you have a set, S0 is in its own set, S1 is in its own set, S2 is in its own set, and S3 is also in its own set. It's actually possible. if somehow the algorithm eventually tells you this is the best equivalent classes I can divide, in that case, what does that really mean? Okay, Raymond. It's the same DFA, exactly. That's exactly true. Okay, you can think about we were given initially S0, S1, S2, S3, four states, and somehow eventually all we can get is basically 1, 2, 3, 4 partitions, right? It's basically the same DFA with 4 states. So this is the case where the input is already the minimum. Is already minimized. Okay, that's something we'll see. Of course, we haven't seen exactly how we can try to refine the partition in an iterative process. It's going to be a while loop, as we'll see. Anyway, so the most important message to get from this slide is try to think about the shape for the cube. Okay, but initially we're going to partition in a way. Let's see exactly what the algorithm says, and then we'll go with that. Okay, let's go back here. Okay. Initially we're just going to say we have P, just say empty set. We're going to use these two variables. They're going to be a swap, in some way. And then T here will just be basically the last refined partition. Basically, we'll start with this. This is a partition we start with. F and Q minus F. Can you try to see what this is trying to do? This is kind of given any DFA, we start with some initial partition. What's kind of the partition we're doing? Yep, accepting and non-accepting or rejecting states, basically. Okay, that's how we start with. Okay, we're going to see diagram. And then we're going to say we're going to compare P and T somehow. You can think about for every iteration, we're actually going to keep trying to find some refined version of P and then store as T. If what we get from T is exactly the same as P, so that means we cannot make any further refinements. In that case, the state condition over here will just be false. That means we exit from the loop, okay, intuitively. Let's see exactly what we should do. Okay, you just do a little bit swap over here. I would say think about why we're doing such initialization and then do the swap over here. Okay, when I run the algorithm, I may not pay attention to this kind of detail, but I will show you the more intuitive way of doing it on the paper. So now, for every iteration, so now we're going to say, we're going to go over every partition in P, right? For every set of states in big P, large P, and then also a small p. For big, you can think about if this is what we have. You can think about this is one possible value for P, small p. This is a second possible value for small p, right? We got two partitions over here. We're going to consider one by one. Okay. And then for every one of them, make sure if the size is actually larger than 1. For size equal to 1, we don't have to consider because they're already the minimum. Okay. So now the idea, this is the most critical line you have to understand. You want to see the current partition, for example, if the partition is actually of size 3. Just give you one example here. If the current partition I'm thinking about, let's say P is equal to, for example, somehow I got S0, S1, S2 over here, and then of course maybe some other. If currently I'm considering this P, which is a member of P, okay, what I need to do is I need to find out for every possible transition, like a character C, right? That's a member of sigma. If I can somehow find out if there's such a C, such that I can find out maybe certain states, for example, S1 and S2, all of them are actually going to lead me to some other states. For example, they might lead me to maybe S4, for example. Okay. On the other hand, by taking C, and then S0 over here, by taking C, it might lead me to maybe S5, different states. And more importantly, S4 and S5, they belong to different partitions. And then in that case, I know that S1, S2 should be considered as equivalents, but S0 should be considered in isolation. In that case, I want to split them. Okay, that's basically the process we're going to do iteratively. Raymond.
The equivalent of only in the ICC?
only in the item C. Well, basically think about this. We keep trying to find out anything that's not equivalence. We don't worry about equivalent just yet. You basically want to split the set out if they turn out to be non-equivalents. We keep doing this until we cannot split out any more non-equivalent classes. That means everything else is equivalence. Yeah, but we'll see concrete example. I just want to mention the algorithm. Okay. Okay. So now let's see the next line. I will see splittable in just a moment. So now basically you want to find out the maximum. Well, I'll explain what the maximum really means in just a moment. And then if somehow we can really split it out, in that case, if you can split it out, you simply put it in. Okay. Basically, think about S over here. If it turns out we can split it out, you can think about this guy here is the S. This is the maximal set to split out. On the other hand, this is the remaining part. So this is like a little p minus S, right? Everything else, they should stay there. You will expect that in the next iteration, you may have to examine S1, S2 again. Maybe there's some other transition that will make them not equivalent, maybe, okay? If not, then they're stable. Okay. Just get some rough idea, we're going to see examples. Okay, and then otherwise, okay, the else part simply means if we cannot split it out, so simply put entire P, so they should remain to be the same partition. So here are some definition. Okay, splittable here. Okay, splittable is simply going to take whatever partition you're considering, and also you want to consider this particular subset, right? It's just some definition over here. You want to make sure, let's go over very quickly. Everything in this particular partition you want to split out, every stay there, if you take this particular C, it's going to lead to the same partition P1. On the other hand, everything else, at least some of them will actually lead to a different partition. In that case, that means they should be separated out. Okay? It's okay. Let's do example right away. Okay? But do you have any question for now? Just any intuition you want to get before I try to go over the algorithm with you? Question?
Why don't you have a case where you have a small c which...
Actually, C is actually just alphabet. What do you mean small c?
Yeah, c, which leads to... I mean, what I'm trying to say, once you have a different type of S for that one for you.
Different type of? What do you mean? So which line? Okay, if you can be a little bit more precise.
So let's say A will lead you, for S1
Mm-hmm.
and S0, A will lead to 1.
Oh, you know what? How about let's go for some example, and then we can discuss that again, since we don't have an example to talk about. Okay, why don't we look at example? Okay, so I would suggest, first of all, we go to the first example. Oh, guys, by the way, sorry. I forgot to mention this for last time, okay? Sorry for the distraction, okay? We actually talked about this last time, okay, for the epsilon N of A. We said that if you have this particular epsilon N of A, I said that you will simply accept sigma star. Actually, that's not true. That's not true, because for this particular epsilon N of A, let's say, for example, if you got simply AB, okay? In that case, will this be accepted by this particular epsilon N of A? If you think about it, initial state can either be here or it can be here. When it is here, can you take A? You cannot take A, so you get stuck. So the resulting set will just be empty. So when you are over here, can you take A? You also cannot take A. So you also get to empty. Okay? So it turns out, if you got only this part here, the only language you can accept would just be epsilon. Okay, I want to mention that. Okay, it should not be sigma star. Just a little bit digression. I want to clarify that. Okay, so when you study the notes from last time, I said sigma star is actually wrong. Okay, it should be only epsilon. Okay, let's go back to the example. Okay. Okay, that's the algorithm over here. We might refer to them a little bit later, but let's just do examples. Okay, let's say this is the D of A. This one is actually from the textbook. So what I would like you to think about is, let me just do it now. How about this? Basically, we are saying that we want to match either FEE or FIE. That's basically the DFA we want to do, right? Basically, you're saying that over here, for every state implicitly, if, okay, let me just make it very precise over here. Okay. For every state we have over here, you might simply go to some dead states. If, I'll just say others over here, which means everything other than F should be rejected to some implicit dead states. Just get it clear. Okay? It's kind of implicit. But the way we drew the DFA in the lecture notes, you should always put every transition for the DFA. Somehow in the textbook, they made the assumption that if the transition is not there, it's undefined, it's as if you went to some dead states. Okay, just make it clear. Okay, good. So now we want to see how we can minimize this particular DFA. Okay, we want to see that. Okay, I'm just going to run the algorithm in a way, hopefully that's intuitive to you. Okay, this is how we're going to do. For simplicity, I'm going to wipe out the transition over here. Okay, but you pretty much get my idea. What I would do is this. I would put this explicit dead states over here. I'll put D here, which means dead states, right? You know where under what circumstances you should go to. So now we want to basically run some iterative process, on the paper. And initially, remember the way we partition is partition between accepting versus non-accepting. Okay. So what I would do is I would say, let's say this guy here, accepting. So that means they have the same color. Whereas for all the others, we got non-accepting. All right, are you okay with that? Okay, very good. So now what we want to see now is to say we want to go for, so far we got two partitions, the pink or the green. Let's say we want to go for every state in the pink. Try to see if we can find out some maximum set of states to split out. Split out in the sense that, okay, for example, let's see. So we're going to go over the possibility of the characters, basically. Okay, let me just make it a little bit smaller so we can accommodate more diagrams over here so you can see the process. Okay, let's go over a little bit more systematically. If I talk about character F, think about for every pink states, by taking F, are they going to go to states in the same partition for F? Let's see here. So now, for example, for S0 is going to, for S0, if I take F, it's now going to S1 in the pink, right? For S1, if I take F, where would it go to? D, in the same partition. What about S2? The same. Okay, what about S4? So F is actually okay. As far as making F is concerned, all the states are considered as equivalents. Are we okay? Any confusion now should raise your hand, please.
What do you mean by equivalent?
Equivalent is more like a relative notation right now. It's more like a dynamic. How about it? Equivalent in the sense that by taking this particular transition here, every pink state is going to go into a state in the same partition. Maybe all of them go to the green partition. That's okay. Or all of them stay in the same pink partition.
By taking it like multiple times, not just once.
Well, it doesn't matter, right? Because if you, okay, here if you take just one single, yeah, just one single character, just one single. Yeah, you don't consider multiple characters. Yeah, it's just single one.
So as long as we're not going to accept the state in the same partition.
No, as long as you're okay. How about this? Basically, you're saying that for every state in the pink, every state in this particular partition, okay, we find that it is the case that S by taking transition C is also going to give you, lead you to the same partition.
We're not going to accept the state, which is
It doesn't have to be accepting as long as it's in the same partition. Yeah. Yeah. Okay, let's try another one. Let's say we consider another one. What about E? Okay, let's see. Okay, sure, let's try. Let me go slowly because that's really important. For S0, if I go for E, where should I go? D. Okay. For S1, if I go E, I should go to S2. Okay. If now in S4, if I go for E, it's going to a different one, right? So now here's the thing. If we want to split out S4, you want to find a maximum in the sense that find out the maximum set of states in the pink that will lead you to the green. Okay, we'll put it this way. Is S4 the only one by taking E that's going to lead you to the green? What's the other one? S2, exactly. Okay, let me repeat again. Okay, we'll just show you the process. I'm thinking aloud. In order for me to really decide as far as E is concerned, okay, I know that for S2, by taking E, it's going to lead me to S3. For S4, by taking E, the same partition. So now, these two should be split out if the other states will lead to a different partition by taking E. That's the case. Oh, let me just finish this, and then I'll come to your question. And then for S1, you can see to go to E, wow, it's now to a different partition, right? It's pink rather than green. And also for S0, it's now going to D, which is also pink, right? Okay. And now, let me just write something down, and I'll take a question. Okay. So now we know that E is not good. Okay. In the not good in the sense that we actually can split out something. Okay. As soon as we find out, we split it out. So now after this, what we will have is basically think about S0, S1, and then S2, S4. And of course, we still got the green. S3, S5. I will show you the visual image in just a moment, but let's just take questions. Question? Oh yeah, of course. You know, we could go iterative. So basically, you can think about for each iteration, we are not too ambitious. As long as you find out the maximum set with respect to a particular character, you can split out right away, and then we delegate to the next iteration to continue. Okay, let's say given this. Okay, so now we're gonna see the following. We are happy with this particular one, right? It's because we found that for E. So what I would do now is this. To show you really what's going to happen here. Okay. Now, I'm going to change the color for S2 and S4. So now we got three partitions, blue, green, and pink. So now, if you run the next iteration, you should really try for every partition again. Okay, so now let's try. Let's still look at the pink. Okay, what about the pink? Just let me walk a little bit faster. Can you tell me if there's any character there that can lead you to different partitions out of the pink? I heard E. Okay, what? Okay, sure. How about just E? Okay, let's say for example, right? Of course, when you implement the algorithm, you might go over transition in a particular order. But now, since we are thinking, so it doesn't matter. We just come up with the idea. Let's say we talk about E over here. Let's see. So E here, S0 should go to the dead states, right? For S1, it should go to the blue, right? It's already different, right? And now, what about S0, S1? Yeah. So that means S1 should be split out. Okay, good, pretty good. So now over here, for E here, we're going to, so this is not good. So what I will do is, especially after this, I should get S4 to be split out. So now I will get S0, S1, okay, and then I should get S2. Oh, sorry, I beg your pardon. Yes, got to be very careful. Thank you. S0 over here. And then S1 was split out. And then we got S2, S4. Those are okay. We'll see. Okay, so now it's easier to see visually. It's kind of fun when you do it. Yeah. Well, of course, you don't have iPad in your quiz, right? Or exam, right? It's not as fun. Okay, so now let's see this. Okay, so now we should split out S1. So now let me change its color, and then orange. Okay, so now we don't have to worry about, So S1, we don't have to worry about the orange partition, it's just one single state, right? So what about the pink for S0? Hmm?
We don't have to worry about it.
Actually, for S0, think about the pink partition. For the pink partition over here, actually, you got two states over here. Do you think these two states are equivalents?
No.
Give me one transition. F, right? In that case, right? Because you know that F is actually going to lead you to an orange, but for D, it's going to lead you to just a D. Okay? So now we got to do further transition. Okay? Let me just make it a little bit more brief. Okay? I don't have any space. I'm going to carry on. So now for this one, I'll just make a note for you. So now we want to, it's the F that we want to change, right? So now let me just copy this guy here. And then go to the next one. Might be easier for me to change the color for this guy here. Red. Red. Okay. Okay, so now S2, S4. Do you think they're fine? Oh, yeah, exactly. Oh, it's a very good point. Okay, let's try that. Okay, first of all, we don't have to worry about pink. We don't have to worry about red. And also, we don't have to worry about orange. They're all singleton set. We don't have to worry. Okay, let's think about this particular partition, right? If you try to say taking E, for example, they'll go to green. Take E, go to green. It's the same partition as far as E is concerned. What if they take anything else? Go to D, exactly. So now, as far as taking transition, a single transition is concerned, they are the same. What about S3, S5? Same thing, right? That's why it's even easier, because you don't have any transition. Everything you take, they might just go to D. So they're also equivalents. So that's the final outcome. But how do we draw that? Okay. The death states, you know how to do it. Basically, just gonna be like that. Yeah, I think the best way for me to do is like this. Let me be consistent with the color. S0 basically is the single partition over here. By taking F, you can go to the orange, which is a single partition over here. And then we have the blue. And in this case, it's going to be either E or I. And then it's going to a states where you got S2 and S4. And then you also get to another state with taking E. It's going to be a state with S3 and S5. And of course, there's going to be accepting states. And then, of course, don't forget, you also got the death states. I'm just ignoring. Okay, you should put that as well. Okay, have we minimized it? According to algorithm, yes, but simply we just got fewer. Okay, you can see 1, 2, 3, 4, 5, 6. Now we got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Okay, 2 states. Well, if you think about percentage, it's quite impressive. Huh?
Wouldn't the set look like it did the step before?
The set? What do you mean the set?
Like the set of sets.
How does it look like? You mean the eventually?
Yeah.
Oh, thinking this way. One thing I want to mention. Let's say if this is the outcome for the current iteration, right? Let's say after current iteration, what you will get. Let me explain the final thing, okay, when you read the algorithm. Because remember, in the algorithm, the state condition over here is to say P must not be equal to T, which means we got some further refinement to do, right? So now if you go back here, over here. So now, according to this, we got the following. S0, S1, and also you got S2, S4, also you got S3, S5. Empty, yeah, everything should be there. I'm just ignoring it, yeah, empty. No, you cannot. Oh, yeah, I tell you what, since I'm just using this example directly from the textbook, okay, basically to really draw the, I tell you what, since it's in the textbook, if you really forgot to include it, it's okay in the quiz. But I will try to make sure the question is clear enough for you. So maybe you should have transition all to the death states. Okay, but we'll see another example. Okay, okay, so here's the point I want to make. Let's say if this is somehow the T I have in the current iteration. Okay? So now let's say I go to the next iteration. And then in the next iteration, first of all, P is going to be assigned to T. And then T will just be initialized to be NT to start with. So now, if we run another iteration of the process, are we going to get the same graph? Yes, because no more further splitting we can do. So that means that, so now after this, you will just get the same set. So that means it's now time to exit. Okay, so this is guaranteed to terminate. The textbook mentions something about fixed point computation. Simply means since every time we split, we are now trying to grow the size of the set. So it's guaranteed to be terminating at some point, but you don't have to worry about it. I just want to give you some intuition here. Okay, guys, any question about this example? Okay, I think we should do another one. That's just the first one. Oh, okay. Okay, by the way, in the exam, or maybe more likely in the exam, if I give you a very complicated graph and give you a huge amount of space, it doesn't really mean you have to proceed for so many steps. It might be that the graph is already minimized. So you got to be able to tell, right? That's really testing your knowledge. How about this one here? Can you minimize it?
No, you can't.
Oh, yeah, why don't we do the initial first together, okay? Okay, initial partition. Oh, so feel free to bring highlighter if later you want to use it in the exam or in the quiz. Feel free, I don't mind. I wish you could. I wish you could. Yeah, I wish you could. Yeah. Huh? Can we not have an exam? Yeah, well, you still need some exam. You still need a... No. You cannot fail the project. Don't worry. It's not 3311. You cannot fail the project. I'm saying that for you, right? Yeah. Good. Okay. Initial partition. Let me say this is blue. Actually 3 accepting states, right? And also 1 non-accepting states. So now, for pink partition, there's nothing we can do. We cannot split it, right? Don't forget, in their algorithm, we say that over here, it should be that the partition should be larger than 1, right? The size, okay? Just remember that. Okay, now for the blue, can we split out anything? Let's try. Okay, just for completeness, let's try. So what transition should you consider? For example, if you consider, for example, A. Oh, by the way, alphabets here is simply ABC. So in theory, we should consider all of them. What about for A? For A here, D1, if you take A, where should I go to? Dead states, okay? For D2, dead states. For D3, also dead states. Good. So now, let's think about, so you can think about or dead. Well, all dead states, well. Okay, all dead is not that good, actually, yeah. Okay, let's think about B here, right? For B, okay, B is more interesting. For D1, you are going to go into D2. For D2, you will go to D2, still blue. For D3, you will go to D2, even though it's different states, but they're all blue. So the same partition. So the idea would be if you are still in the same partition, you're fine. Okay. You know what? Just for those of you who are a little bit concerned, I'll write it down just for your convenience, right? When we talk about B, when you're in D1, by taking B, you're going to D2. And if you're in D2, if you take B, you're going to D2. You're in D3, taking B, you're going to D2. Am I right? Yes. Okay, the same states, but more importantly, they're all blue. Okay, that's important. Okay, what about C? The same, okay, let's see. Yeah, for now, for C over here, for D1, by taking C, it's going to D3. Agree? D3 here. And now for D2, if you take C, it's going to D3. D3 over here, taking C, also D3. Well, just happen to be the same state, but as long as it's in the same partition, you're fine. Okay, we have considered for every character in the alphabet, A, B, and C, we cannot really find any unequivalent behavior. So that means we cannot split it. So that means this is exactly the result. Okay, surprising? No? Okay, sure.
Does this algorithm guarantee minimization?
It's guaranteed. The textbook doesn't really provide any proof, but I believe in case you're curious, they give a name for this particular algorithm. If you Google that, maybe you can find some proof. Yeah, but it's guaranteed. The intuition will be you start with partition, and then you try to split out the partition when you find any unequivalent behavior. As soon as you find out, there's no more splitting out you can do, so that means everything remaining is equivalence. That's the intuition.
One question would be, is there, like, these are small examples.
Yeah.
For, like, very large examples, is there guaranteed to be one minimum DFA? Does not necessarily. Like there's a minimum size, but it could be multiple different.
So yeah, I see what you mean. To be honest, I'm not too sure. The question was, is guaranteed to give you the DFA? Number one is equivalent behavior. Number two, it's a minimum in the number of states. There might be another DFA with the same number of states. That's also minimum.
So when you want to prove that, like,
I guess, yeah. So that's why we didn't really go through the proof. Yeah, could be interesting for 2001 or even later. Yes, question.
So wouldn't we still be minimizing this since we're summarizing each set into one node?
Oh, basically, thinking this way. Are we still?
well, you can take one
Mhm.
Two sets instead of.
like basically merge D1, D2.
But isn't it a particular pattern?
Oh, actually, you know what? I think you might be right? Since we cannot split this further, in that case, we only got pink and also we got blue. Agree? So now, that means over here, oh, actually, you might be right. Yeah, you guys are good, right? Yeah, sorry. Yeah, so we got this guy over here, the 0, okay, starting states, and then over here, and then you take A, and then you go to this particular blue one, and that one there is going to be D1, D2, and D3. And for which, taking A, B, or C will just be the same. Well, B and C will be a self loop, for sure. And then, of course, A will be going to the dead states, right? Something like that, yeah. Yeah, you're right, it can be minimized, yeah.
But is it equivalent? I'm not sure.
Because I think it's a particular pattern.
Yo,
Anything you take out the D1 is accepted. So as well, you just accept it even you go to D1. Any move you take out the D1 is accepted. A or B.
yeah, basically, somehow, you see, once you take the initial A, you're basically saying, after that, any A or B or C will be accepted anyway.
Like any patterns of B's and C's in any order.
And B and C, yeah, that's correct. That's correct. Yeah, basically, I think that this might be a little bit contrived example created by the textbook. It's saying the following. After you take this initial A, and then for this particular partition over here, it doesn't matter you take B or C. You're still remaining in the same partition they're all accepting. Only A will take you out to the dead states, so that's fine. Yeah. Hey, guys, I'm so sorry. So this definitely is not minimal just yet. So you should really have a 2 states. Okay. Chelsea, you okay? Okay, I want to make sure. Yes. Okay. Can we do one more? Aha, fun, right? Okay. This one I got it from the web, right? Okay. Okay, I think this one is a little bit more like a normal DFA that we are used to. How about I give you a little bit opportunity to practice, just 2 minutes. Why don't you try? Okay. I can tell you that you can definitely minimize that further. Okay. Maybe, guys, I think for this one here, let me try to be a little bit more considerate, considering that you may not bring the highlighter for the quizzes, right? Let me try to just draw circles around to see if that might work. Let's see. May not be as intuitive, but let's try. But you do it first, and then I'll do it together with you. That'll be the last example, and then I'll give you a little bit exercise to do. Apparently, for the whole algorithm, just for your information, the part that might be the most important. Oh, I'm sorry. Let me mention that quickly. Sorry about that. Yeah, okay. So for the whole algorithm, what you really want to make sure if you want to implement it is it's splittable. Apparently, that's a critical routine. Okay. Anyway, sorry about that. Yeah, let's take 2 or 3 minutes. Okay.
You need like a minute just to write.
Huh?
You need just a minute to copy this.
I wish there's a way you can copy, right? Yeah. Well, you just give it a try. You know. Yeah. I don't want to. I thought this is fun, actually, this algorithm. Yeah, try to go with maybe some iteration, okay, and then we can do it together, okay. I'm not sure if that might be feasible in 2001 to say once you cover a particular algorithm, you just ask students to implement it in Java. Anyway, just some suggestion. Aha, you're done. Okay, good. Okay, whatever answer is. Okay, let's take another 1 minute, okay, to see how much progress you can make. If you're struggling a little bit, that's good. That means you haven't really fully grasped the idea. Try it, and then drop by my office hour on Wednesday if you got some trouble. Okay, another 30 seconds, and then we'll do it together, right? Just check to see if I'm doing the right thing. I could be wrong, you might be right. Yeah, okay, you found that. Yeah. Okay, all I'm gonna do, I'll just start with the initial partition. I would say initially, I will put Q4 questions?
So we have to write the entire thing, or is it just enough to draw a diagram?
Yeah, I think, okay, let's be feasible. Let's say you're given this particular question, how are you supposed to present it, right? You know what, let me think about it, yeah? Apparently it's not gonna be covered in your quiz number 1. Let me think about how you might present it. But I think most importantly, let's get it first. Yeah, if you can suggest something.
One way you could do, which would kind of be a hint, but also not really, you could like provide a bunch of copies of the diagram,
Yeah.
but not as many as there are steps. Because if you give as many as there are steps, and that
I might give you 10, for example. I'll say up to 10 iterations, yeah. If I give you exactly 3, you might think, oh, maybe I should only need 3, right? Yeah. Yeah, I see what you mean. Yeah. 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 That's fair. I think so. Yeah. If I can think about better one, I'll suggest. That sounds reasonable. Okay, let's do it together. Okay. Okay, so allow me, I'm still going to use a highlighter, just easier. Q4, Q1, and Q2. And then Q3, Q0, and Q5. Okay, let's look at the pink. Can we split out anything for the pink?
Yes.
Oh, I heard yes. Okay, tell me which transition.
transition
Okay, I trust you. Let's say 1. Let's try that. Let's say for Q3, if you do 1, you go to the blue. And for Q0, you do 1, you also go to the blue. But now for Q5, aha, if you take 1, you actually go to pink. Okay, let me write it down. Okay, it's our last example, so let me just write it down. Basically, for Q3, by taking 1, you go to Q4, which is blue. And now, if you try to go to Q0, you take 1, and then you also go to Q1, also blue. And then for Q5, if you take 1, you're going back to Q5, right? Basically, think about pink, and these two are blue. So you split out. Split out Q3 and Q0, okay? Oh, that was your question beforehand. Okay, so now we got it, right? Good. Okay, so now let me just do that. Maybe that's the only thing we got to do. Maybe. I don't know. Okay, so now what I would do is Q4 and Q1 should be separate out. Oh. Oh, yeah, yes. I'm so. Yes, it is. Again, I said I could be wrong, right? Now you see why, right? Okay. Oh, yeah, exactly. So Q3, Q0 should be different. Yeah, exactly. Let me change the color, right? You see what I meant? Yeah. I'm so glad I don't need to take exam on this. Yeah. Okay, Q3, Q0. Okay? Okay, so now, are we in a stable state where no further splitting can be made? Okay, so now it will be an exercise for you. Okay? So I would say if you believe this is really the final state you are in, you don't have to go over every transition to show me, as long as you're confident. But I would say in doing the quiz with the exam, you have to say, if I want to split out, for example, I'll show you one. If you want to split out Q3 and Q0, you should at least show me this kind of step so I would know how you decide that. Right? And also Q5 should remain to be in pink, right? At least I want to show this. Okay? But now let's say you're already here. I think that's right. I did it yesterday. So if you're already here, now you cannot make any further split. You can simply say no further split can be made, and you believe that's a minimum. Of course, if it turns out you're wrong, there's some further you can make, you just get partial marks, right? Guys, any question about this algorithm here? You can see I didn't really go step by step. That could be too tedious. I think that might be the best way to understand. But now, once you get an intuition, go back to the algorithm to see how it works. Question? No, you cannot get rid of it. You still need the dead states. Remember DFA, basically you want to make sure for example here. I agree with you, first of all, Q5 is like a dead state, right? Once you get to it, there's no way to escape. If you don't have that state, that's going to be a problem. Because now, for Q4, if you simply take one, where should you go to? For DFA, for every state, it should be defined for every possible transition. The textbook just being lazy. They simply don't really put in the dead states. But when you do your implementation, it should be there. Yeah. Okay, the question was, is it possible to get rid of Q5? No. If you got a dead state, you should put it there. Go ahead. Oh, you know what? I believe it should. To be honest with you, I can check the documentation. I believe it should. Basically, you can think about every lexer, they call it. Lexer or lexer generator. If you just give regular expression like specification, we're going to do some in-class tutorial maybe in the week before the reading week so you can get ready for the projects. Okay? Let me just finish this and then before your next question. So now you got regular expression here, lexer, and then you can think about now it's going to generate a code for you to use. But you can assume somehow this particular process over here is going to be maybe from regular expression to epsilon n of a, and then to d of a, and also to minimize it. You can assume they do it. They should. They should. Huh? What if they don't? Change another tool, right? Yeah, sure, yeah.
Is it free to use?
Answer? Yeah, it's free. It's free. Yeah. I'll try to see either we can do the demo in-class demo. Either maybe we can do it earlier. I'm thinking at least we cover a little bit grammar before we can do it. Yeah. We'll do it on in-class tutorial. When we do it, I'll ask you to bring your laptop. Okay. Okay. Not yet. I'll let you know. Okay, guys. Any question about this algorithm here? I think it's worth doing. Okay. Okay. Let's go back here. At least you learned something theoretically new. Okay, these are the three examples we just went through. Okay, so now at the bottom here, I got two exercises for you. Number one, if you try to go here, okay, if I click on here, I'm now in 50A, right? Okay, remember previously we did this particular DFA for the epsilon NFA, right? Try to see if you can minimize this particular DFA. Exercise number one, okay? And then let me go back to 58. Second exercise for you is this. Second exercise is if you just go to the textbook, for page 59, Q1 and Q2, I think also worth doing. So you got 3 more exercises, 3 more, okay? And 1 more. This will be more like a complete example. Let's say I have a regular expression for you. Let's say it's basically about to specify the pattern of a register name. Let's say you got R. R should be verbatim, the character R, followed by 1 or more occurrences of 0 or 9, let's say. Okay? So now, can you say, given this particular regular expression, first of all, put it into the epsilon NFA, and then using subset construction to go to DFA, and then apply the minimum procedure to minimize the states, okay? A few procedures. This could be one possible exam question I would like to ask. I might just give you this particular regular expression, and then the next 2 pages, I would say, come up with the DFA that's minimized. Yes?
Do we have to do the epsilon NFA? Or if we know, like for example, this one, it's easy enough to even do the DFA directly yourself.
I would say it depends on how I ask you the question. Most likely, I would like to see the whole process. Because in general, in some special cases, yes, you might go directly. Mm-hmm. Yeah. Yeah, but I would say it depends on the question. But I would say if in the exam, I might just say just do the process anyway. Question.
When you mean classes, it's when you have to have 1 or more.
Yeah, 1 or more. So that means after the R, over here, after the R, you want to have at least 1 digits, 1 or more, basically. Okay, so I think you got a few exercises to do. Okay, so don't worry, it's not covered on Wednesday. Okay. Okay, good. Final topic for scanner, quickly. This one is rather easy, but just want to give you some vague knowledge. I'll say vague because it's not exactly implemented precisely, but at least gives an idea. So now, for scanner, basically, the source language, let's say Java, you basically want to have a list of syntactic categories. For example, you may have keywords, you may have white spaces, you may have different stuff. For example, this is something we talked about previously. One syntactic category could be the keyword for while loop, while. That's one category. And another one could be identifiers for a class, for methods, etc. So that would be another category. And then for white spaces would be another category, right? So now, your scanner event, the first gate for your compiler, they should really try to identify all of them. How? How can we have a single DFA and somehow it can recognize any word that's going to satisfy either of the category? Let's say, for example, for our particular language, we only got 3 categories. Either it's a while, or it's an identifier, or white spaces. So we got 3 categories. How do we actually come up with a DFA that is able to accept if it matches either of the category? I'll go with you first and then Ash. Go ahead.
Would be just a transition for each token for the acceptance?
Sure, you definitely want to identify token, right? Token by token. But somehow, how do you know this token belongs to this particular category and another token belongs to maybe another category?
You use epsilon to categorize.
Okay, epsilon, okay. You're basically talking about the second stage, right? You can use epsilon to say either or that, right? Okay, Raymond.
I was going to say, like, using epsilon NFA and then at the end it'll figure out which is the right one, right?
You know what? I would say, why don't we start with the front end? So think about the user of the compiler, they should really specify regular expression. So how do we do that, Ash?
Well, using the regular expression language that we have.
Yeah.
Specify all this stuff.
Yeah, basically, do you specify all at one go or you specify individually?
If you do it individually, then on the compiler side, you can have like, I don't know, because it's a finite number of categories.
Yeah.
You can have like additional like bits or something.
Something like that, exactly.
Which category you're in.
Yeah. That's exactly right. So basically, you're going to get a finite number of syntactic categories for any source language you have. It cannot be infinite. So this is a general pattern. Separation concern. You will specify each category separately, first of all, and then combine them together using plus, like a union, right? So thinking this way. Think about for syntactic category number 1, using regular expression R1. And then union with another category. And depending on how many categories you have, that's general. So n over here is guaranteed to be finite. So think about eventually we're going to get a union of these regular expression, and then you now know how the trick of turning that into a single DFA. That's minimized. Question?
You also want to take care of like while matches the identifier. Like instead of identifier with someone who was wild, you have to check that it's not a keyword. If it just matches that, doesn't mean
Oh, I see what you mean. That's a very good point. If I understood correctly, you're saying that, for example, if we are reading in while, we want to make sure it's a keyword while rather than identifier while. It's a very good question. Very good. So it's more like it's more like something you can specify such heuristics for the compiler. So okay, it's very good. So let me just mention this, and I'll take your question. Okay. So the question is like this. Your name? Oh, Coco. Interesting. Good name. That's a good name. Yeah. Okay, so let's say this. Let's say you got basically while as one category. Okay? You got another category of identifier. Okay? These are the two different categories. Okay? You want to make sure when the user actually gives you, let's say if this is the program you have, right? If somehow you put while over here, while should be treated as the while over here in this category rather than in the identifier. Okay? The easiest way to do this is in the parser generator that we're going to talk about. You simply say the higher you specify that, the higher priority it is. Okay? For example, I might say I want to make sure I have while over here first, and then I will put down the regular expression for identifier. Think about if you talk about the specification for the scanner. This is something we'll see later in the in-class tutorial. I'm saying I specify this pattern first, which means the scanner will always try to match while if possible. If it cannot succeed, then you'll go for the next one. So there's priority over there, precedence. Yeah. So what you're concerned about is not a real concern. They will resolve for you. Question?
But also, more realistically, is it not even the concern of the scanner, right? They just have to match one of the patterns or the other. But then the parser has to, like, based on the grammar.
Yeah, I think,
determine, like,
yeah.
which pattern.
So what we're going to show you as the code for the scanner wouldn't really cover this precedence issue. I think it has to be adapted with some coding to really handle this. I'm just saying, later on when you use this, you should remember the higher you specify the pattern, the more priority you will take. Yeah. Question?
I haven't used Java in a while, but I feel like
You will use it a lot. Yeah, later. Yeah.
I was wondering, like, whenever you type while in Java, regardless of what you're typing for, it's always considered to be a keyword, right? So like it doesn't really matter. You just always assume that when you type while, it's not an identifier, it's a keyword for the while.
Yeah, exactly. Because it will be identified, right?
Yes, you don't have to like.
You can think about.
You guys as a compiler always assume that when you type while.
Yes, the reason that, let's say in Eclipse, as soon as you type while, it will be highlighted, right? It's because the scanner will see, oh, since you got while, so it can be matched to be matching this particular syntactic category, so it will be just while.
And then they tell you like you can't make a variable.
Yes, unless, do this experiment quickly, right? If you try to type in Eclipse, if you say while over here, right? As soon as, let's say up to here, if you simply put a space, you'll find that it's highlighted right away. Okay, on the other hand, if you try while over here, let's say 12, it wouldn't be highlighted. Because what a scanner will try to do is to find the longest unbreakable string that's going to match a particular category. And now, while is not the longest one. You still got 1 and 2 afterwards without any delimiter for the white spaces. So now, while 12 will be a valid identifier. Okay, make sense? Great. Good. Good. It's kind of interesting.
How would you distinguish in Java if I print while, like system out, like while? How does it in a quote?
Oh, you say, oh yeah, exactly, yeah.
And you can have space before and after while. Still, before that.
Oh, I see what you mean. It's a very,
that's my final answer.
No, but spaces should be spaces.
okay, Mahu actually got a very good question. What he's asking is this. Let's say I'm typing in Eclipse. Again, I say start with a quote, and then maybe with a space, doesn't matter. Let's say 2 spaces. And then if I try while, and then put another space, you'll find that it's highlighted right away. Okay, on the other hand, if you try while over here, right? As soon as you type while, it will be highlighted. Because what a scanner will try to do is to find the longest unbreakable string that's going to match a particular category. And now, while 12 will be a valid identifier. Okay, make sense? it's not going to highlight while, which means the compiler recognizes while is not supposed to be a keyword while. Why? Simply because somehow the code over here tells you. Okay? Somehow the scanner knows that as soon as you see some beginning code, that means whatever you're trying to do over here, unless it's escape sequence, in this case, it's not, right? Once you see the code, you know that whatever that's going to happen after that, until the ending code, is going to be retrieved verbatim. So it's not going to be a keyword. Somehow they will decide that. Yeah.
What if you have a while followed by a curly bracket?
It's a different, it's more like about grammar. If you, okay, good question. Let's say in Eclipse, if you do while, let's say followed by a space, okay, and then you do curly bracket, for example, right? If you do that, they belong to two different syntactic categories. So the while over here belongs to one category. I'll say category 1. Maybe the category for loop. And then for this one here, it's just another category. And then it's for maybe just opening delimiter.
No, my question is, there's no white space between them.
Doesn't matter? Oh, I see. Oh, it's a very good question. And that will link exactly to what I want to talk about, okay? The Miskov question was this. If you do while over here, let's say this. I put exactly this. No white space, okay? Basically, what's going to happen is, up to here, what's going to happen is this. After exactly over here, we thought category number 1, like this, is already matched. However, since we got more to be matched, so we want to go a little bit further. As soon as we find out this particular opening curly brackets, you will find out the following. While together with opening curly bracket itself does not belong to any category. First of all, it's not a keyword. It's also not an identifier, because identifier cannot contain, for example, opening curly brackets. So now what should we do? We should roll back. Roll back, what it meant was this. We're going to see this in the algorithm. So when you were here, while you already matched one category, but now we decided to go further. But if you go further with this, you find that it will lead us to some error states in the DFA, because we simply don't have a string like this, a word like this that can be recognized. So now that means, now before we can proceed further, we'll simply say this guy here should be the longest word that can match a syntactic category that we should return. You will see exactly this concept over here in the algorithm. Guys, in case you're a little bit confused, I think that's a good example. Let me write it down, okay? So now, basically thinking this way. While, when you are here, okay, this already recognizes while, as a valid token. If we go on to include curly brackets, okay, I'll go a little bit further here, which means while curly brackets, this particular string does not belong to any syntactic category. So that means it will be in an error state. In that case, we had to roll back. No category. That means rollback. Okay, we'll see exactly how rollback work in just a moment. Okay, it's something you should just be aware of. So just about how things work, at a very basic level. Okay, any more questions? Okay, we're good. All right, let's go a little bit further. Okay, principle of a scanner, one word at a time, and then you should find the longest possible character sequence to match a pattern. And sometimes if you go too far, so that you reach an error state, you roll back. That's exactly what we're going to see in just a moment. And also, you may want to specify priority, like what Coco said, right? You should set the priority. Okay, we got 10 minutes. Okay, let's at least finish this, right? Okay, so now the algorithm, let's just give one example. That's from the textbook. Let's say this. Let's say we have a syntactic category called register, let's say. It's going to be the category for register names. Okay? And then, let's say this is regular expression. Well, that's one of your exercises, right? You get partial solution to this over here. Let's say this is our regular expression, okay? That's what you will have to specify for the compiler, okay? In order to generate a scanner for you. And then, let's say this is the minimized DFA you should get when you do the exercise, okay? So when you check your solution, that's what you will see, okay? So this is already the minimized DFA. Of course, there's another death state, which is not specified here. So now, how do we go from here into some working scanner code? So now, the textbook provided 3 possible implementation: table-driven, direct-coded, and also hand-coded. We'll just talk about table-driven, okay, just for some idea. Okay. Let's say this. We got 3 tables. Is it readable at least? Okay. Basically, for this one here, we're saying it's called classifier. It's saying that whenever you're reading R as a transition, it's basically like a register. Okay. And then whenever you read anything between 0 and 9, it should be a digits. And then if you read about end of file, it should be like other category. If you read about other, just other. Okay, just like a category, like a table. And we got transition. This one's easy, but notice one thing. Okay, you can see that the number of columns over here actually correspond to the category we have over here, right? You can see over here, how many categories do we have? We got register, we got digits, and we got other. Only 3 categories. That is why you only got 3 columns over here, as opposed to maybe 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, just in a single column, just for digits. Okay, just 2 different tables. Okay, you got another table here. That's for eventually, let's say if I'm in accepting states for S2, for example, you can see S2 is accepting states. That means I can now tell you that the token I'm matching belongs to a register name. Okay. We're going to do one or 2 examples to run through, okay, just to get you comfortable with that. Any questions about this? Okay, good. Let me just go over very quickly about the code structure. Okay, 4 stages. Okay, you will see rollback somewhere over there. Okay, okay. Stage number 1, you will simply just initialize your states and also the word you have read so far, just epsilon to begin with. And also, in order to roll back, you need a stack. Okay, so you got an empty stack to begin with, and then you simply put bad over here. It's not exactly type correct, it's just pseudocode. Okay, you can think about the bad is just at the bottom of the stack to actually tell you if your input string eventually is actually invalid. Okay, so that's stage number 1, initialization. Stage number 2, we're going to basically keep running through the character by character for the string. Okay, so question for you. When should we exit from this particular while loop? When you're in the death states. Right? Oh, sorry, I forgot to explain. SE over here stands for error states. Okay, sorry, I forgot to explain that. SE, so as soon as the current state is actually an error state, that means now we're going too far. We should roll back. So draw some connection to the previous one. If when you are reading, after reading the while, you should be in an accepting state. But since you want to go further, if you go further with this particular opening curly brackets, you will enter some error states. So now that means you should stop scanning and roll back to where you just finished reading the while. So that should be the syntactic category. Okay, I'm so glad you mentioned that example, right? Such a nice example to talk about. Okay, so now, basically we one by one. So now the only thing I want to mention to you is about how to do the transition. Okay, so we're gonna keep pushing the states. Okay, and then there's a little bit in direction over here. Okay, the way you look up in the transition table is this. Based on the character over here, you're gonna look up to see which category it belongs to. So it's called cat. And then you're going to use this cat over here to do the transition. I'll show you one example. It's not difficult, okay? Just in direction. Okay. Okay, so now this one, rollback. Okay, this one is saying So while, well, basically state is not a member of the accepting states, and also state is not equal to bad. Okay. So now, while it is the case, right, we're gonna try to roll back. So when will we exit from the loop? When either state is equal to bad, which means we're at the bottom of the stack, okay? Or the state is simply a member of the accepting states, right? Okay, basically like that. Okay, we're gonna pop and then go roll back. I'll just do one example together with you, okay? And then we're gonna do this particular one. We're gonna say if, finally, once we are done with this, and then we say if state is actually accepting, and then we just return what's the syntactic category, okay? And then otherwise we say it's invalid. Okay. Anyways, don't think that's too difficult. It's just a little bit low level. So that's why I don't want to spend too much time on that. Okay. You know what? I think we only got about 4 minutes left. In order for me to do the 2 examples, it might take about 10. Okay. How about this? I will suggest the following. Okay. That's the end of the scanner lecture over here. I would say, let me just briefly mention for the parser very quickly. Okay. Just draw some context. And then we'll finish that example in the beginning of Wednesday, and then we'll go on to the parser. That'll be chapter 3. Okay. Oh, but for Wednesday, make sure you show up in time. We'll do the quiz in the beginning of the lecture. In the beginning, not at the end. If you show up after 15 minutes, too bad. Okay. If I arrive late, that's okay, right? As soon as I arrive, we'll start. Okay. All right. All right. Let's see. You know what? I'll just let you go earlier today. We only got 3 minutes. Okay. We'll start from here on Wednesday.